Appreciated. We are going to move on to Dr. Peter Ciesielski. He's going to be speaking about co-production of bio-derived fuels, chemicals, and materials. Dr. Peter, when you're ready, please continue.
Okay, thanks a lot, and I just want to thank Tom for giving that great overview, and now we're going to take kind of a deeper dive, and I'll provide some more specific examples of products that we're making here at NREL. So I've basically entitled this talk, and I'm going to pose a lot of this as a question of what should we do with biomass? And so I like to kind of introduce this concept with this cartoon, and this really is an age-old question. So how do we decide the fate of biomass between fuels, chemicals, and materials? And I love this cartoon. I found it on the internet. It really illustrates how humans have probably been struggling with this question for a very long time. And so the first caveman here on the upper left, he has invented fire. So he's invented biofuels. He's learned how to burn wood, which is great. He's very excited. And then his buddy comes up and has invented a materials application for biomass, which is this club. And so if you look, you know, the moral of the story here is that the guy with the club actually ends up winning. And so it just kind of speaks to the fact that materials applications of biomass are something that's very important. Moving forward, I just want to talk about essentially what biomass is and why it's so valuable to us. So biomass, and here I'm talking about specifically lignocellulosic biomass, so not the starch and corn and so on that's so easy to convert into fuel. I'm talking about this is really the structural component of biomass. And so if you look at this material down at the nanoscale, you see that it really is a fantastic composite material. So it's a composite of three major biopolymers. So the primary structural component are cellulose fibrils, and so they're assembled into these nanofibrils that often bundle, and then that material is essentially cross-linked with hemicellulose, which is another polysaccharide, and then everything is kind of backfilled in with lignin, which is essentially an amorphous aromatic type polymer. And so biomass is really, I would say, the most successful example of fiber-reinforced nanocomposite materials on the planet. I mean, this material, this structure, is the reason why giant sequoias can grow as tall as they do and still transport water, hundreds of feet in the air. And so it really is a successful material on planet Earth. And the other important thing to remember from an energy standpoint is that the biopolymers that I've just described to you, these are direct embodiments of stored solar energy and reduced carbon dioxide. So every single carbon atom that ends up in plants started out as CO2, and it took photons from the sun to assemble this material into the state that it's in. And so another thing to remember is that regardless of what we do, this material is mass-produced on planet Earth. And so it's a very important resource for us to understand and to utilize in the most effective way that we can. So people have been using biomass for a lot of different applications for a very long time. And people have been making money from biomass for a very long time as well. And so historically, the most profitable applications of biomass, the most profitable products have been material applications in nature. So the big ones are lumber, like wood for construction materials, paper, and cotton textiles. So these are the big ones. For example, perhaps the most lucrative form of biomass is high-value construction material. So if any of you are sitting in your nice comfy office right now and you have an expensive wooden desk, that material, as the wood in that desk, is worth many orders of magnitude more in a material state than it would be if you were to deconstruct it and make ethanol from it. Many orders of magnitude. In fact, it would be a very bad capital venture to undertake that. But I mean, that's probably obvious. So the applications that I'm going to call economically challenged, so these are things that it's been much more difficult to make money on, are converting lignocellulosic biomass into transportation fuels, commodity chemicals, and drop-in replacements. And so these are things like the three lignocellulosic or cellulosic biorefineries that Tom mentioned, they're really doing the extremely difficult work of breaking down biomass, which is a very strong, very robust, we tend to use the word recalcitrant material. And it's a lot of hard work and it's a lot of energy to break that material down into monomers that you can then turn into fuels, liquid fuels, and chemicals, and drop-in replacement type molecules. And so I'll categorize these for you. So the historically profitable applications of biomass have really used intact biopolymers, and the ones that have been more economically challenged to date are deconstruction products, so depolymerization products of the biopolymers and biomass. And so really the moral of the story is that deconstructing these biopolymers all the way down to monomers, it's challenging. It's a very complicated process, as Tom gave a nice overview of a few slides ago. It can be expensive, and from an energy standpoint, it's actually energetically inefficient to do this in many cases, because what you're doing is all the free energy that's caught up in those polymer bonds, you're essentially forfeiting that as you break it down to monomers. And so all the free energy, the stored solar energy that's caught up in those polymer bonds is forfeited if you deconstruct this material all the way down to monomers. So I'll give an example of why this, an example of when someone has tried to commercialize this. And so probably many of you are aware of this Coke's, what they call the plant bottle. And so this material, they start with cellulosic biomass, which is certainly a noble effort. They then completely depolymerize all of the biopolymers, specifically the carbohydrate components, down to monomeric sugars. So that in itself is expensive. They then convert those sugars through a multi-step catalytic process to ethylene terephthalate, which they then repolymerize all the way back up to make PET. And so I'm calling this the scenic route to biomaterials from biomass, because you start with polymers that are actually pretty good to begin with, break them all the way down into sugars, do multiple expensive catalytic steps, purification and so on, and then repolymerize. So this is certainly plant derived, but it's not a very efficient way or a very profitable way, evidently, to get to renewable materials from biomass. So I'll offer you perhaps a new paradigm here. So the question is can we still produce renewable fuels and chemicals? We definitely want renewable fuels. We definitely want renewable chemicals, as Tom made a great case for previously. But can we do that with more and preserve some more valuable material products from biomass? And the answer is yes. We're beginning to arrive at routes to do exactly that. And it's really these strategies have been facilitated by really our enhanced knowledge of biomass. Now, it used to be we could decide the fate of biomass based on, well, is this a nice type of wood, or is this just scrap wood, or is this a valuable fiber for rope, or is this just something that we're going to compost? So, but now we're to the point where we can look at the individual biopolymers and biomass, and even certain classes within those biopolymers at the nanoscale and the molecular scale, and make those types of decisions. So. One strategy I'm going to talk about here is the co-production of nanocellulose. So these are nanoparticles from cellulose and sugars via enzymatic saccharification. And so the idea here is that you can depolymerize all but the most crystalline forms of cellulose fibrils. And so all those depolymerization products can go for your fuel and chemical applications, and then you're left with these nice nanoscale building blocks, so nanoparticles from cellulose, which have a lot of very neat applications. And I'll talk just a little bit about those here in the next couple slides. I would propose to you all that nanocellulose is a potential happy medium. You need to do some deconstruction to get down there. You can use all the deconstruction products for fuels and chemicals, but then you end up with this fantastic nanomaterial that really has two manifestations. One of them is cellulose nanofibrils, and these materials have dimensions similar to carbon nanotubes, and they are often present in big bundles depending on how you do the processing. And so they're excellent for filtration applications, for fiber reinforcing of polymers, And then if you deconstruct those even further down, you do additional hydrolysis, you can get down to these cellulose nanocrystals, which is shown here in the micrograph in the bottom left, which are these shard-like nanoparticles. And all this came from lignocellulosic biomass. So it has this, in comparison to kind of the conventional nanomaterials, these have a lot of advantages. They have the potential for mass production. I mean, you can make these things at the scale of pulp and paper. So you can really mass produce these things at a much lower cost compared to conventional nanomaterials. They're biocompatible. These materials are actually edible. They're eco-friendly. Their end of life is fantastic. These things will be eventually digested by enzymes. So certainly biodegradable, and they have a bunch of useful functionality, which I won't be able to describe in detail for time limitations today. But I just want to quickly say what we're doing with nanocellulose here at NREL. So in addition to developing processes where we can co-produce them alongside biofuels and biochemicals, we're building bio-inspired materials from these things. And so the application I'm going to talk about briefly is using kind of a brick and mortar technique that biology tends to use quite often to make materials, where you have kind of a nanoparticle type brick, if you will, that is held together with a mortar. And so this application here is a mollusk shell, where the bricks are calcium carbonate and the mortar is protein. So we have kind of drawn inspiration from that and developed a similar approach, where we use cellulose nanomaterials as our bricks and other plant-derived sugars and carbohydrate polymers and other small molecules from plants as the mortar. And so we can make these cool composite materials completely from plant-based materials. So I'll show you one here. So you have to look closely. So this is a nice piece of wood sitting in the background, and then in the foreground there's a small plastic film that's leaning up against it. And so this film was made completely from cellulose materials. It behaves similar to polyethylene. It has fantastic mechanical properties. The one difference is it has a thermal stability about twice that of polyethylene. And the other thing, it's completely biodegradable, and even this material has the advantage of being marine degradable. So if this ends up in the ocean, it degrades just fine, and it'll serve as food for crustaceans. So these are some materials applications that we're certainly excited about. Okay, so I'll just skip to my conclusions now. So to answer the question, what should we do with biomass? Preserving the free energy in biomass, and so that means using intact biopolymers for materials applications where it's applicable is generally a good idea. I mean, it's energy efficient at a pretty high level. And so I'll just remind you that historically, materials applications of intact biomass have been the most profitable. Okay, so next, deconstructing biomass all the way down to monomers is inexpensive and often inefficient. And if you want to do this, you should have a very good reason to do it. And by a good reason, I mean you should do very careful economic analysis to make sure that you're targeting products that you're going to be able to sell for profit. And then finally, controlled selective deconstruction, choosing which aspects of biomass should be depolymerized, I think should emerge as an important goal for future biorefineries. And finally, renewable materials from intact biopolymers like nanocellulose are emerging as promising functional replacements for a lot of petroleum-derived materials. So that's all I want to say, and I'll take questions at this time if we have time. Otherwise, I'll answer them later.
Thank you, Dr. Ciesielski. We'll give it a minute here to see if anyone submits a question for you. Otherwise, please keep the submissions coming, and we will have Dr. Ciesielski answer them offline while our next presenter starts things up.